Welcome. This is a Math 100 midterm review, and this is part 1, a chapter 1 review. And the problems that I'm doing are from page 105 in the current edition of the Math 100 book. The first question says, solve for the indicated variable, and the first equation, part A, says solve p equals 20h minus 120 for h. So if I'm going to solve for h, what I'll do is I'll add 120 on both sides. I'm going to try to isolate this term. So I'll write p plus 120 equals 20h, and then I can divide both sides by 20 because this is a 20 factor times h. So p plus 120, divide the whole thing by 20, and I've isolated h. So there's the solution to that. In the next one it says solve a equals p times 1 plus r over n for r. So if I'm solving for r, there's actually two ways you could go about it. The very first step, you could either distribute the p or we could divide both sides by p. I think I'll take that route, although the other way is just as good and also give you the answer. And in fact, the answer could look slightly different depending on that choice you make right here, but there are several ways that we could write the answer. So let's get this p factor out of here. I'm going to say divide both sides by p, because I'm trying to isolate the r. So I can do that because this is p times a factor, I can divide by p, divide the whole thing by p, and these factors of p here cancel out. And so we have a divided by p equals 1 plus r. Now the r over n is a term because it's added with the 1, and since 1 is added as a term, I can subtract 1 from both sides. So my next step would be to subtract 1 from both sides. I'd have a over p minus 1 equals r over n. And finally, to isolate r, because n is a factor since it's divided, and factors are things that are multiplied and divided. The n is a factor, I can remove that factor by doing the opposite operation, which is to multiply. So I'm going to multiply both sides by n. This is an n. I'm multiplying both sides. And really I need the parenthesis here because that indicates that the whole entire left-hand side is getting multiplied by n. And then you could either multiply it in or not. The thing is that I've now isolated r. So I've essentially got the answer here. r is equal to n times a divided by p minus 1 in parentheses, like that. Now this isn't the only way to write it. In fact, when I look at the key in the back of the book and the answers, they've actually written it differently. Now the answer that I have here is correct, but we could see other ways to write that. Let me use the space right up here just to demonstrate that the answer could be written other ways. We have from below, r is the quantity n times a over p minus 1, and there's a variety of ways we could write it. We could distribute the n, multiplying it times the first and second terms, and we could write n times a all over p minus n, and this is correct and this is correct. And then we could also get a common denominator. So if we got a common denominator, we'd say n times a over p minus, now if I put a p in the denominator, I have to multiply the top by p, so I could write n times p like this. Now I wouldn't put a check mark next to this, although it's correct. The point of getting the two fractions with a common denominator is to then simplify it into a single expression with p in the denominator, and then n a minus np could be in the numerator, and yep, that's fine. But I noticed that I could actually factor out the n. In fact, what I could have done at the very beginning is to get a common denominator here. So let's say n with the quantity a minus p and then p in the denominator. I could write it this way. So this is the way it's written in the back of the book in the answers. So both of these are correct ways of writing an expression for r. Doing it this way, you realize that what would happen is that it would have been a different situation if I had distributed the p and then come back and divided by that p later. It would have looked like this. Okay, so that's the end of that one. Let's move on to question C. That's still part of number 1, and it looks like this. Solve 3/4 less than 1/7 minus 3/2 x less than or equal to 9/5 for x. Okay, essentially it's like you can think of this as if I've got two inequalities. The inequality here that I'm solving, and if I was solving just this inequality, specifically that inequality there, I could minus 1/7 from both sides. But if I was solving this inequality, specifically that one, I could also minus 1/7 from both sides. So in effect, I'm going to minus 1/7 from both sides at the same time. Or in fact, actually, probably a better thing to do is I could multiply both sides of an inequality by a common denominator, something that would clear all the fractions. So why don't we do that first? Let's get rid of, because every single one of these terms has a fraction and all the denominators are different. We'll start dealing with having to get common denominators as we move forward. Let's just take care of it all at once, one step. So I'm going to look for one number that will be a common denominator with all of these denominators, and I'm going to multiply both sides of both inequalities, that is, all three parts, by that number to cancel all the fractions. So something that all of these would go into, I need a factor of 4, 7, that makes 28. I've already got the factor of 2 and the 28, and I need a factor of 5. Basically what I'm doing is getting an LCM, which requires to have a 4, a 7, it's already got 2, and it's got to have a 5. So 28 times 5 is 140. So I'm going to multiply both sides by 140. Be careful to include the little line here. That's going to make a small difference in the very end whether I include the boundary value or not. Here I don't include it. Here with the equal I will include the boundary value. So I'm multiplying by 140 times 9 over 5. Now the whole purpose of the 140 was to be able to cancel fractions. So the 4 goes into 140. You could just divide 140 divided by 4. And that's 35 times. So 35 times 3 makes 105. When I distribute the 140 to both terms, I have 140 divided by 7, which is 20. And then the 2 goes into 140 and then multiplied by 3, so I got 140, divide that in half. Of course, that's 70 times 3 is 210, so minus 210x. And then over here, 140 divided by 5 is 28 times 9. This is 28. Multiply the 28 times 9, you get 252. Alright, so that was a bunch of fractions there, but it's all done. All the fractions are done. Now I can move on to isolating this x term without worrying about any more fractions. So here's where I'll look at this inequality and minus 20 from both sides on this inequality, but then also minus 20 on both sides of the other inequality, so effectively minusing 20 from all three parts. So 105 minus 20 is 85. And then 252 minus 20 is 232. Okay, now I want to get rid of this negative 210. So I'm going to divide, because it's a factor, I'm going to divide by negative 210 because I want to get a 1x there. So I divide both sides of both inequalities by negative 210. And now, immediately when that happens, these inequalities have to change. But it's sort of not convenient to change them right now because they're already written. So what I'll do is just on the next line, I'll reverse the directions of the inequality. So you could say it's technically incorrect. As soon as that negative's there, these things should be changing directions. I'm going to correct it in the next line. So 85 divided by 210. To keep the answer exact, which will match what we see in the back of the book, they have it exact. That is the actual fraction. You see, if you go in the calculator and you type it in, 85 divided by 210, you're going to get a decimal, which 85 divided by 210 gives me a decimal that goes on for quite a few places, and I'd have to round off to make it in decimal. So to keep it exact, I'm going to look for a greatest common factor here. I know that clearly I can divide them both by 5. So 85 divided by 5, that's 17 in the numerator, and 210 divided by 5, that's 42. And it's customary to write the negative in the middle or on top, so I'll write it on top. So I've got negative 17 divided by 42, and I've changed the direction of the inequality here, and then again change the direction of the inequality. 232 divided by 210. Let's see if we can reduce that into an exact fraction. It can at least divide by a 2, so let's start with that. 232 divided by 2, 116 in the numerator, and 210, that would be divided by 2, that would be 105. Now let's see, the easier of these to factor for me, I can see the 105 I can divide by 5. So let's see, 105 divided by 5 is like 21. So 105 factors into 3 times 7 times 5. So the only thing I'm interested in, can I divide 116 by 3? And if I go 6, 7, 8, no, that's 8. Cannot divide by 3. Or you could just check on your calculator. Can't divide by 3. What about 7? Can you divide that by 7? 116, I'll just use a calculator. Doesn't divide by 7. It clearly doesn't divide by 5. So this is reduced. And so I'll write it that way. Negative 116 over 105. This way I'm keeping it the exact value rather than putting a decimal and then rounding it off with a decimal and no longer being exactly correct. I'm able to keep the exact answer. Now, the fact that we have x bigger than this negative, it's sort of customary to put the smaller number on the left, so it's convenient, although technically correct here, kind of convenient for reading, to change the order in which it's written. And also it says specifically in the question, it says write the answer in interval notation. So it would not be correct as it's written here because it's not an interval notation. So I could get the interval notation from this, but it's convenient to write it one more time with inequalities in the sort of customary order to say x is going to be greater than this value, and oops, no equal, just strictly less. Okay, from this I can write the interval notation. I'm going to use a square bracket. That square bracket means to include the boundary. This is the lower boundary of an interval because we have x bigger than or equal to this number, but all the way up, but not equal to that number. So negative 116 over 105, all the way up to negative 17 over 42, but I'm not including that boundary value, so I use a parenthesis. And that's the answer in interval notation. All right, let's move on to question number 2. Estimate f at negative 2. So at negative 2, that means I'm looking for, when x is negative 2, what's the y value? And I'm going to estimate that it's right there between negative 4 and negative 6. So I'm going to answer negative 5. That is, f at negative 2 is negative 5. Question B, estimate all x's where f of x is 3. So this is a y value. When you write f of x, you're actually giving a range value, which is typically a y value, and that's what we have here. So when the y value is 3, looking at a y value of 3, I'm going to say, maybe right here, Now the answer in the key says -4, and I can see why -4. I'm trying to make it come out to be -4. You may have estimated, I mean we're estimating here, and you may have estimated -4.1 or -4.2 or something like that. And I'm going to say that -4 is a reasonable estimate. So x equal -4 is my answer for B. Now, I don't think you're going to come up with any other value, because to have the y value equal 3, it really looks like it's not going to include any other x value over here, just only the one x value of -4. For question C, the domain. Well, the domain is the interval of x values on which the function is defined. So I would say that it begins here at -5 and it finishes at 3. Now, this is just a really big dot to emphasize that point. I don't think the domain is intended to go past 3. Looking in the answer key, that's what they say, stopping at 3. That's only because this dot is so big to emphasize where it occurs, but there are no values of the function that go beyond 3. So, and anyway, again, it's an estimate, so we could have interpreted maybe 3.1 or something if we wanted to. That wouldn't really be wrong, but a very good reasonable estimate is from -5 up to 3, and then I'm going to include the square brackets because of those dots. That means in the dot there, indicating that that point is included as a point for which the function is defined. Otherwise, there could be like an open circle, which means it's defined up to that value but not at that value. So this is my answer for C, from -5 up to +3, including both boundary values. Estimate the range. Well, that's the y values for which the function is defined, all the y values from the lowest to the biggest. So it looks like the lowest is -6, roughly. You could estimate slightly below that, but I'm going to go with -6 up to +6, and I'm going to stay at +6 just because that's where that dot is. It's just an overly huge dot just to emphasize the point. So let's go from -6 to 6 as our estimate, again including the boundaries. So that's my answer for D. Estimate the x-intercepts. Okay, what I'm doing now is looking for points where the function y value is 0. Those are my x-intercepts. So I have a place where it crosses the x-axis. These are the x-intercepts, where it crosses the x-axis, intercepts the x-axis. So that would be like maybe -3.2, maybe -3.3. So writing the x-intercepts, as I got two of them, we'll write them as points. So it's not an interval, it's a single point. And sometimes we use parentheses for the boundaries of an interval that are specifying an interval, but here I'm going to use the parentheses for an ordered pair. -3.3, 0. That's one single intercept, and the other x-intercept right here, which is an x value, and I'll write it as an ordered pair, 1, 0, and then the y-intercepts, or for a function you'd only have one y-intercept, and this is a function, so it's going to cross here at, looks like -2 on the y scale, so I'll write 0, -2 if I write it as an ordered pair. And that's the answer for E. Okay, number 3 says the amount of interest earned annually, I, on a deposit is directly proportional to that deposit, or principal, P. If $1.76 is earned, $1.76 in interest is earned annually on a principal investment of $27, find the function I of P that relates interest earned and use it to find the principal investment that yields an annual interest income of $66. So we'll first do this directly proportional. When you say directly proportional, or when you see or read directly proportional, that is going to set up an equation that has this basic kind of form, although in this case I'll write it as interest proportional to the principal amount. I'll use letters that are indicating the meanings of the variables. So if we start with that, interest is directly proportional to the principal, and then we have some particular values in that relation, we can find the constant of proportionality, k. So we have $1.76 interest that is earned when the principal is 27. So $27 earns me $1.76 in interest. I can find the value of k, 1.76. If I divide by 27, I'll know that constant k. That constant k would be the same now for any principal and any corresponding interest. So 1.76 divided by 27 is roughly 0.065. So let's go 0.065 is k. So we just round off to 0.065, and so now I can take the model and write the constant in there. The model relates in interest and principal with this direct constant of proportionality. So now the question is, use this to find the principal investment that yields an annual interest of 66. So if the interest is 66, then I could find out what P would have to be. So $66 divide by that constant 0.065, and that'll give me the value of P. That's 1015, let's say 38 cents. All right, moving on to number 4. Find the solutions to the following equations algebraically. Give the decimal answer rounded to 2 decimal places where needed. Question A. We'll start by distributing, collecting like terms, and then moving all the x's onto one side. So I'll get 6x plus 15 plus 7 equals, on the right hand side, 22 plus 6x. And well, okay, what's going to happen at this point? You can, well, first you could combine the like terms, although you could tell the answer already. You see, I've got 6x plus 22 equals 22 plus 6x. And that means that any value of x is going to make this true. These are always true. This is what you could call an identity. I noticed it immediately here when I said, oh, I'm going to minus 6x from both sides, but then that cancels. I've got 22 equals 22, which is always true. So it doesn't really matter what the x value is. And so what you have to write as the answer is all real numbers. All right, now moving on to part B. We'll do 4.14 minus, now the 3 times 2.6, this is 7.8, and then the minus 3 times the minus 5, that's a plus 15. On the right hand side we have 6.9x, and then minus x, and then plus 1. Because we're distributing this negative 1 factor here. All right, now we can combine 4.14 and plus 15. That gives me 19.14 minus the 7.8x. And on the right hand side I have 6.9x. Take away 1x gives me 5.9x plus 1. And now we want to combine all the x's on one side and all the constants on the other. It doesn't really matter which side. It's perfectly fine if we add 7.8x on both sides here, so that we could just add these. So we'll have on the left hand side 19.14 equals, and now I have to add 5.9 and 7.8. That gives me 13.7. And there's still a plus 1 over here. And then we get minus 1 from both sides. So I have 18.14 equals 13.7x. And then if we divide both sides by 13.7, What do you get with 18.14 divided by 13.7? 18.14 divided by 13.7 is about 1.32 if you round off to 2 decimal places. 1.32. There's the end of that one. Moving on to number 5. For Darla and Daisy's profit function, P of h is 20h minus 20. That sort of sounds like number 1. Yeah, that was a profit function actually in number 1. Well, let's calculate P of 25. So that means just plug in 25. 20 times 25 minus 120. 2 25s, that's 50 times 10, that's 500. So that's the value of the function at 25, and the meaning is their profit is $380. Part B, solve the equation P of h equal 450. So if we set 450 as the range value for the function, then the equation looks like this. So to solve this equation, I'm going to add 120 on both sides. So I have 570 is 20h, and that means the h has to be 570 divided by 20, or half of 57, which is 28.5. So that's the answer to this part of the question. Write a sentence to interpret the meaning. Now, sentence would be the profit is 450 if the hours worked is 28.5. Number 6 says, set up a linear system of equations for the following application problem. Remember to follow the steps of problem solving. Don't forget to declare your variables. Use the elimination method to solve the system, and remember to write complete sentences for your solution. Mathematics marshmallow cereal is 30% oats, while Lucky Calculation cereal is 65% oats. How many ounces of each cereal need to be combined to get 20 ounces of a yummy mix that's 50% oats? So I have to apologize right here for the names of these. It's ridiculous. But never minding that, let's go on. X will be the cereal, and X measures ounces. And also make a note that this is 30% oats. I'm going to say Y is the ounces of the LC cereal, Lucky Calculations. And Lucky Calculations is 65% oats. How many ounces of each one need to be combined to get 20 ounces of some yummy mix that's 50% oats? I think the easiest equation to see first is that when you add the two cereals together, it's going to be 20 ounces. So X represents the number of ounces of the first cereal, and Y is the number of ounces of the second cereal. And when you add those together, you need to have 20 ounces to meet the condition stated in the question. And the other one is going to depend on the actual amount of oats. And so what you could do is you could say, well, the amount of oats is going to be the same throughout. Mixing it together doesn't produce more oats or get rid of oats. What the equation actually needs to be is 30% of X is the actual amount in oats, right? Because 30% of the X ounces is the actual amount of oats. And then you look at the amount of oats that comes from the LC cereal. That says it's 65% oats. So 65% of the ounces are the actual amount of oats. So the actual amount of oats that come from the cereal and the actual amount of oats that come from the LC cereal, adding those two together has to be the actual amount of oats that you have in this yummy mix at the end. And it has to be 50% oats, and it has to be 20 ounces. And so you could say 50% of the 20. Or, of course, we could just write 10 ounces of oats. So this whole system, I'm going to rewrite it now. The first equation doesn't really need to do anything to change that. The second one could simplify and write 0.3x and 0.65y, but then simplify that to write it as 0.5 times 20, or 10. Alright, so that's the system of equations that I need to solve. It's two equations with two variables. Both equations are linear in x and y. We can use the elimination method, as they say in the directions, to solve this. So what we could do is we multiply the top equation by a negative 0.3 all the way through on both sides. It would still be equal and consistent, therefore, with the given equation, but we could then use that to add to the other equation and eliminate x. So let's do that. So multiplying the top by a negative 0.3 and just leaving the bottom equation alone creates a new system that's still the equivalent, like it's equivalent equations, but it's written in a new way in which I can eliminate the x's. This becomes negative 0.3x minus 0.3y. One of the things, a very easy thing to make a mistake of, is that you have to multiply both sides by whatever you're using. Here I'm going to multiply both sides by negative 0.3. So 0.3 times 20 gives me 6, and it's going to be a negative 6. Now I can add these two equations together. If both sides are equal, I could add something that's equal on either side of something that's equal, and what I get is a new equation that has to be equal, but the benefit of that new equation is that x is gone in this new equation. I've got 0.65 minus 0.3y, so that's going to be 0.35y. Basically 0.65 minus 0.30. So 0.35y equals, well, I'm just adding, so I get 4. And over here when you add, they cancel. So the y has to be 4 divided by 0.35. 4 divided by 0.35 is like 11.43 if you round off to 2 places, ounces. And now that I know the y value, I could go back to any equation in this system, it has to be true, and use the y value to get the x. So the easiest one is back to the original where I have x plus y equal 20. So we could say x plus the y, which is 11.43, has to be 20. So the x is 20 minus the 11.43. This is going to be 8.57 ounces. And the directions told me I had to write this in complete sentences. So mix 8.57 ounces of whatever was X. That was the cereal. 11.43 ounces of the LC cereal. And that's the answer for this one, number 6. Okay, number 7 says, use the graphical method to solve this system of equations. What that means is that I'm going to graph both of these two lines and look to see whether they have an intersection or not, and if they do have an intersection, that would be the solution to the system. Now, especially graphing on the computer like this, my graph just isn't going to be perfect, and this is really no way to know exactly the solution. The best thing about doing it this way is that it just gives some understanding as to what the solution actually means, or if there even is one, and what that means. This wouldn't really be an efficient way of getting the solution. I'll be doing a lot of extra work to do the graph, and I'll only have an estimate of the solution. If I really wanted the solution only, and I was interested in the most accurate way of getting it, I would use either substitution or elimination to solve this algebraically, and I wouldn't use the graph at all. Again, the graph just helps to interpret the meaning of the solution. So let's look at this. In fact, sometimes it's helpful to kind of label the lines, like line A and line B. What we're doing as we continue on from this point is assuming that both of these equations are true, and if they're both true, what would that imply? So if line A is in fact an equation that is given as a true statement, then there are infinitely many x's and y's that make this equation true. So let's get a picture of all those points, which is what we do when we graph the line. And of course, because it's a line, I only need 2 points. How about if I get intercepts? I'll make x equals 0. If x is 0, the y is 3/2, or 1.5. And if y is 0, then the x is 3. And this gives me 2 points, the intercepts for line A. So here's the point 0, 3/2, and there's 3, 0, and this is line A. Now is going to go through those 2 points. For line B, I'll make x equals 0, find the y-intercept, make y 0, get the x-intercept. If I make x equals 0, then I get 6/5 for y, which is like 1.2. If I put y is 0, then I get x is 6/4, that's 3/2 for the x. So here's 1, 2, a y value of 1.2 roughly. Okay, there's the 2 lines, and this is where they intersect, and really the fact that it's not clear at all. I mean, it could be -1 for the x, and it could be 2. Estimate of intersection -1, 2. That is close to the solution. It might actually be the solution. What I could do now to confirm this is either actually plug it in for x and y in both equations and see if in fact it actually works, or I could solve it algebraically and get the answer that way. I think the one that's the less work is to actually plug it in and see if it actually works. If I plugged in -1, 2 to equation A, I have -1 plus 2 times 2, which is -1 plus 4, and that's 3, so that looks pretty good. It doesn't guarantee until I've made sure that it worked in both of them. Second equation, 4. If I plug in -1, 5, plug in y is 2. Yeah, this is going to be -4 plus 10, which is 6. And so this is the exact solution, which I actually found using the graph. Actually, this is part A for number 7. So let's go on to part B. Number 7, part B. Okay, so number 7, part B, it says use elimination. So I don't really have to do the graph. Of course, we could do the graph again and use that as an estimate. We might even be able to guess the actual solution with the graph. But we're doing only algebra here. We don't need the graph to solve. We're going to find the one point that makes both of these equations true, which is essentially finding the one point that's actually on both lines, if there is one. In fact, there could be the 2 lines never cross, or the 2 lines could be actually the same line, and therefore all the points on that line are solutions. I could tell right away that it's not going to be the same line because these coefficients are not ratios. They're the 2 to 3 and then the 3 to 5 ratio is different, so the slopes aren't the same. So should be, so they're going to cross somewhere where they have different slopes like this. All right, so the elimination method, what that says is I'm either going to multiply one equation or the other one, or maybe both of them by some number so that I can get either the x's or the y's to have the same value with an opposite sign as the coefficient in each equation. Then I can add the 2 equations together and get a new equation that I can solve for the one variable. Let's eliminate x. So I'll multiply the top equation by a -3 and the bottom equation by a 2. And that way On top I have a minus 6x, on the bottom I have a positive 6x, and then when I add the equations, the x's will cancel out, and I'll have only y's. Make sure you multiply both sides of the equation. Now, when I have this left-hand side, negative 6x minus 9y is the same as negative 15, I'm going to add that same quantity on both sides of something that's equal, and I'll get something that's equal. So basically I'm adding the two equations together. The x's are going to cancel out. This is 1y equal negative 65. And then once I have the y value, I can solve with any equation from this system and get the x value. Or if I had found the x first, I could use that and get the y value. All right, so let's take the first equation because it doesn't really seem to be any advantage to any one of them. Let's go 2x plus 3 times the value of y that we know. So I'm using this equation. This is equal to 5. 2x plus 3 times y, where I know the y value, has to be 5 if this equation is true. Could just as well use the second one, or even any of these, because they all have to be true. 2x plus 3 times 65 is 180 plus 15 is 195, negative. And here's the answer. We could write it as a point, 100 comma negative 65, or you could just say x is 100, y is negative 65. Let's move on now. Question C. Okay, in number 7, part C, we're going to use elimination to solve the system. System we're solving is 7x minus 3y equal 21 and x minus 5y equal negative 6. So we could multiply the bottom equation by a negative 7 so that we're able to cancel out the x's. So you leave the top equation alone, multiply the bottom equation by negative 7, make sure you multiply both sides by negative 7. And this way, when you add the two equations, x cancels out, you get 32y equals 63. Divide both sides by 32, and you have the y is 63 over 32. Now what I'm doing here is looking to see if there's any common factors, anything I can cancel with 63 over 32. And I see that 63, that's 9 times 7, 32, that's 8 times 4. So I realize, okay, wait a minute, there's no common factor here. It's not going to reduce. None of that really matters. I'm going to leave it as 63 over 32. And I'm going to leave it that way because that's the exact value. Rather than putting in the calculator and getting a decimal and rounding off the decimal and not being exactly correct, it's really preferable to be exactly correct in a situation like this. It's not a word problem where I might want to translate it into something practical. I don't have any reason to be in decimal and rounding. I can be exactly correct when I write it as a fraction. So I'm going to use that fraction now and move on and find the x value. I can go back to any one of these equations and plug in the y value and get the x. So I think I'll use this equation here. X minus 5 times the value of y that I know, 63 over 32, has to be negative 6. Now, to find the x and to have an exact value, I'm going to get rid of the fraction rather than dividing and rounding off. If I divide on the calculator, round off, I have a decimal. It's no longer exact, and for many, and maybe most situations, it's fine to have the decimal and round off. But I want the exact value here. So let's do 5 times 63, 315. So we'll have x minus 315 over 32 equals negative 6. Well, actually what we could do is we could just add that on the other side. We don't really have, I was going to say multiply both sides by 32, but it's just as easy here just to go right for the x and then get a common denominator. 6 times 32, 192, negative 192. So that's the x value. And we could write the answer as a point as well. That is the point of intersection. It's the point where these two lines are going to actually cross. We could get the calculator, get these in decimal, and you could check to see that the decimal answer, if you got a decimal, you could compare it with the decimal value of these. Okay, number 8. Average concert ticket price was $40 in 2000 and $60 in 2004. Let P be the ticket price and T be the number of years since 2000. Use the formula slope equals change in P over change in T to calculate and interpret the meaning of the slope of this line. So we're assuming a straight line through these 2 points. That is an average rate of growth in the ticket price that we can find with this formula. That's what the slope is. So the slope is the average rate of change. It's the change in the price. 60 minus 40, that's a $20 increase over 4 years. You could say from 4 years, 2004 to the start, which is 2000. Or 2004 minus 2000, it's the same thing. You're going to have 4 on the bottom. So you really have $20 increase in 4 years. So that's, notice the units here, $20 in 4 years. And it's positive. So it's a $20 increase per 4 years, which you could reduce to a $5 increase per year, assuming an average rate of change. Okay, we're going to use that part A answer in part B. Part B says use the point slope formula to find the linear function that gives price P in terms of T. So point slope is y minus y1 equals m times x minus x1, where x1, y1, this is x1, y1 is a known point, one specific point on the line, and m, of course, is the slope. So in this particular example, the one point that I'll use could be either of these points, that in the year 2000 the price was 40, or in the year 2000 the price was 60. Those are both. I could use either one, and the slope that I'll use, of course, is this $5 per year steady average increase in the price. So let's write the formula. In this case, we could say P minus P1. So any price minus a particular price would be the slope times any time minus a particular time that goes with the P1. So we could go, if you want to pick, it doesn't matter which point. There's 2 points here. I could say that the year 0, the price was 40, and I could call that my T1 and that my P1. Or I could use this. In the year 4 years after 2000, the price was 60. Either point, both will give me the same answer in the end. Let's go with the first one here. It's always nice to use 0 if you can, because there will be one less term. So P minus 40, a slope of 5, T minus 0. So that means P minus 40 is just 5 times T, and therefore P is 5T plus 40. And we can put a box around or a circle around that. Just note that also we could say that P is a function of T and write it this way. And you could double check, if you put in 0 time, that's the year 2000, the price would be 40. And if you put in, let's say, 4 years later, that's 5 times 4, that's 20, plus the 40 gives me 60. So this function is doing what it's supposed to do. It passes through those 2 points, and it is a line. So that must be the answer. All right, that's the end of number 8. Let's move on to 9. Okay, number 9 says find domain, range, slope, y-intercept, and x-intercept for the linear equation 2x equals 30, and sketch. Alright, well, this particular equation is linear, but it's linear with only one variable, and so we are either going to have a vertical or horizontal line. In this case, we have a vertical line because we have a constant x value, so it can only go up and down on those particular x values. Let's simplify the equation. If we have 2x equal 30, that's equivalent to x equal 15. These two equations have the same solution. So the equation is really just x equal 15, and a graph is very easy to make. We can say 5, 10, 15, 20. Because we have a constant 15, we get a vertical line. The domain, you could sort of give two answers here. In one sense, you could just say it's not even a function. It doesn't have a domain. The answer in the back of the book, what does it say? Yeah, another possibility is you could just say the only x value is this 15. So that's fine. As far as the interval of all x values, that's another way of looking at the domain. The interval of all x values for which this curve is defined is, well, there's only one x value, and that's 15. And the range is all real numbers. You could put like that, or as in interval notation, you could say minus infinity to infinity. The x-intercept, that's pretty clear. That's the point where it crosses the x-axis, which is the point 15, 0. So this is not an interval. This is a single point, 15, 0. And the y-intercept, well, that's pretty clear. Also, where does it cross the y-axis? It doesn't. None would be the best answer there. Also, the slope. Every vertical line will always have an undefined slope. And so you could make the conclusion immediately when you see that it's an x equal constant vertical line. The slope has to be undefined. If you try to take 2 points on the line to calculate the slope, you can see why it's undefined. If you subtract y values, you could just take any other point. Let's say this is 15, 15. Or let me use another one. Let's say this is 20. So this would be the point 15, 20, and this is the point 15, 0 here. And if I took, see, I'm taking any 2 points on the line, so I'll take these 2 points. So if I subtract the y's on top, and it doesn't matter what order, and subtract the x's on the bottom, of course that's the issue right there. 15 minus 15, this makes it 20 over 0, and that's undefined. As soon as you divide by 0, you have undefined. So that's it. That's the answer for number 9. And finally, number 10. Number 10 says, Martha's Antiques sells old Victorian doorknobs for $7.99 each. Martha finds these old doorknobs at the flea market for only 50 cents each. She has fixed monthly expenses of $1,700. Let X be the number of doorknobs sold. Show all work for the following. A, find the revenue function, then we'll find the cost function, the profit function, and graph the profit function. Part D says Martha would like to earn $1,000 profit each month. Graph the line P equals 1,000 on your graph above and use the TI-84 to find the number of doorknobs that Martha needs to sell to meet her dream of $1,000 monthly profit, and label that solution on your graph. So getting to part A, the revenue. Revenue is the money that's brought in, and if she's selling them for $7.99 each, we could say that the revenue function is the price times the number sold, and that's the revenue function. Question B, find the cost function. Well, the cost function is fixed. It doesn't matter how many she sells, so here, cost will be just a fixed $1,700 per month, but this is not per month. This is just X is the number of doorknobs. So we're looking at revenue and cost in the context of each month. So this is the cost function. So find the profit function and graph it and sketch it. Seems like that's kind of redundant. So the profit is always the revenue minus the cost. The money you bring in minus the money that you send out. So the profit function is 7.99x minus 1,700, and those are not like terms. It's as simple as that. It's not going to combine. So now we'll move on to graphing this one on the next page. So if I'm graphing this, The typical thing to do with a graph would be to have intercepts, and we could start with a t-chart like this, plugging in 0 for each of these points. If x is 0, you've got negative 1700 for the profit. If we don't sell anything, we still have to pay the costs, which means in that particular month we'd lose $1,700. And when the profit is 0, this is the break-even point. I have to solve for that one. If I put 0 in for p, I have 7.99x minus 1700. Solving for x, I'd add 1700 to both sides. 1700 divided by 7.99 is about 212.77. So let's say about 212.8. So roughly 213. Because we're talking about doorknobs, not fractions of a doorknob, let's just round it off to the nearest whole number. We'll say break even when you sell 213. If you sell 213 doorknobs, you've just covered the costs, just slightly over, basically zero profit. And those 2 points now can translate into points on the graph. The vertical scale is profit. Now there's negative and positive profit, but there really isn't negative number of doorknobs, so there really isn't any point to have points to the left of that axis. This is X, doorknobs sold. This is profit. Profit looks like we should maybe count in thousands, and looks like we could count maybe in hundreds or in 50s on the horizontal scale. And might be able to make it look better if we counted by 500s on the vertical scale. So let's do that. Now it doesn't make sense to have the line continue to the left with negative values of x, but it does of course make sense to continue this way because this is selling more and more doorknobs with a larger and larger profit. So that should get an arrow, but I won't put an arrow here. This is the break-even point. It's the X-Intercept. In this case, it's about 213. I'll just rounding off. It's not exactly 213, but in this context it makes sense to round off even to a whole number. This is the Y, or actually P-intercept right here, and that one I have exact. That's 0 minus 1700. And that one in the context of this problem is if you sell 0 doorknobs, you still have you have a profit of negative 1700. You still have a cost, which means your profit is a total loss of $1,700. Okay, so I find the profit function here, and I've graphed the profit function. And that's the end of part C. Let's move on to part D. Part D is here. It says Martha would like to earn $1,000 profit each month. So let's graph the line P equals 1,000 on your graph above and use the TI-84 to find the number of doorknobs that Martha needs to sell to meet her dream of $1,000 monthly profit. I'll label this solution on the graph. Well, we don't really need the TI-84 at all. I can do it, show you what that would look like, but it's completely unnecessary to have a calculator. This is something we should definitely be able to do without the calculator. I think it's faster to do without the calculator. Let's begin by graphing that line, P equal 1,000. So here's the line P equal 1,000. It should be a horizontal line, so as straight as I can make it. And of course that's where the lines cross, and that point is where she's finding the right number of doorknobs to sell to hit that $1,000 profit. This is actually the intersection of two lines, which means that I'm really solving a system of equations. Just one of those equations is a very simple equation. So to find that point now, completely without a calculator, totally unnecessary, what I'm going to do is just say I want P equal 1,000 and P equals 7.99x minus 1700. I want both of those to be true. This is a system of equations where I can solve, but rather than using elimination, it's even easier to just use substitution, to substitute 1000 in for the profit. So if the profit is 1000, then what would the x have to be to make the profit 1000? You see, I can get the exact value algebraically. Even with the calculator, I'm potentially getting an approximation. So we'll add 1700 on both sides. So that's 2700 equals 7.99x, right? Because I added 1700 here and added 1700 over on the other side of the equal. These terms are canceling out. And now I'm going to divide both sides by 7.99. So 2700 divided by 7.99. Basically, because of her cost of $1,700, and she wants to make a $1,000 profit, she really wants to make $2,700 for the month. At about $8 a doorknob, you're dividing $2,700, the total revenue that she would need, divided by the price that she's selling them at, to how many doorknobs. So $2,700 divided by 7.99. This is about 337.9. I'm going to round it off because it's doorknobs. I'm going to say 338 is x. And so that answers this question, how many, find the number of doorknobs that she needs to sell to make that $1,000, and label the point on the graph. That would be this point right here. It's roughly 338. The exact point is in decimal that we'd have to round off, but in terms of whole number doorknobs, we'll say 338 comma 1000 is that point of intersection. Okay, and that answers that question. Let's look at the picture on the calculator. Okay, so to demonstrate this on the graphing calculator, I'm going to use this website, Semtech, maybe, semtech.net. You can Google TI-84 emulator. Actually, what I'm using is an 83 emulator because I happen to have a ROM, which is a little program available to simulate the TI-83, but not the 84. Just at a quick moment's notice here, I found this one. Oh, it's essentially the same on the 83 and 84. We're going to graph really two lines on here. So let's do that. So the first line that I'm graphing is this 7.99 x minus 1700. That was the profit function. So I'm typing in 7.99 x minus 1700. And this is in the Y editor, so you hit the Y equals to type that in. Now you need to think about a reasonable window for this. So remember, I was going from like negative 1700 up to around 300 or 212, something like that was where it crossed. That was the X-Intercept. So and I know that about 338 was the X value that she had to sell to make $1,000 profit. So set the window like this. I hit window, you go from maybe, let's go from 0 to maybe 500. And we can count by 50s, so that's the X scale. And then the Y minimum, I want that to be, let's say, negative 2,000 up to about 2,000. And then you can count by whatever you want, but let's maybe go by 500 for the Y scale. So here's the graph, and I want to type in the profit equal to 1,000, that horizontal line. So in the Y editor, the second line, I can just make it 1,000 and graph that. There's that line, and then what I'm trying to do now is figure out what's this point. We could do that by finding an intersection of the two lines. So let's go hit the second. You see that the calc button here right above trace, I go second calc, and I'm looking for an intersection, so I could type number 5 or just scroll down. So the first curve, let's take that line as the first curve, so hit enter. Second curve, yeah, that's my second curve. And what's a guess for about where they cross? It's right about here. And so 337.9 in decimal is a very accurate value for where those two lines cross. So that's why we came up with an answer about 338 as the number of doorknobs that you would need to sell to make $1,000 monthly profit. By the way, while I'm here looking at this, I could also show you, like, we'll do second calc and go for number 2, the 0. So to find the 0, I'm hitting this, it's tracing this, so I'm looking for the 0 of this line. I want to know where it's equal to 0. That's called the 0 of the function. So a left bound, a little to the left of that 0, and then I go a little to the right of that 0, and enter that, and then give it a guess in that interval right around there, and it finds 212.7. Remember, I rounded off, said about 213 was the break-even point, so that's that point as well. All right, so that ends that demo on the calculator, and you can see that the results that I had in my graph match that result that I found on the calculator. Okay, we've got 2 more examples. Let's move on to number 11. Number 11 says the following table shows estimated annual costs for annual cost of raising a child in 2001 for a family with an income above $65,800. So we have a table, ages of the child, annual expenditures. Question A, identify the variables. Okay, for identifying the variables, you could really use any variable you want. You could go with X and Y, kind of the standard. You can also use letters that might be suggestive of the meaning of the variable that sort of help keep track of what's what. Let's do that. We'll say A is the age of the child, and E is the expenditure or cost. It's important to make the connection that A should be the independent variable, basically what would normally often be X, and then the E should be the dependent variable, what's often the Y, the output value, the range value. So the domain sort of the function is age, and for each age there's an expenditure. Okay, part B says use the methods of this section to find the linear regression model that best fits the given data set. So we'll go back to the calculator then and find a line that will fit this data. Alright, so here's my calculator. I'm going to use the TI-83 Plus. It's essentially the same on the 84. And the data I have here, I'm going to put this data into the calculator. I'm going to use the Stat button. So click here on Stat, and then what we want to do is edit the stat data. So hit Enter. Okay, if you actually had data in the table already, what you could do is just hit the up arrow to go to the top header of the column, and then hit clear at that point. So now I'm going to type in for list 1, L1, I'll put in the age of the child. And then you can hit the right arrow to scroll over to the second column and enter in all of the annual expenditures in L2, list number 2. Obviously we want to be very careful to make sure we've typed in everything exactly correct. Okay, so now once I have the data in, what I'm going to do is go to back to Stat and do a calculation. So I'll just move over one and look at this column here, or this header, calc, and then choose number 4. So either you can scroll down or just type in 4, linear regression, and hit Enter. And you could just hit Enter again right now and get basically the information that we need, which is A now is the slope actually, and B is the Y-intercept or the E-intercept actually in this particular example. And you could write those things down on a piece of paper and then use that as you continue. But actually you can also have the calculator store it right away automatically for you in the Y editor. So let's do that. So I'll hit Stat again, go back to a calculation with the stat data, go down to linear regression again. But instead of just hitting Enter, what you could do is give it 3 arguments for this sort of function call. What I mean is you're going to type in L1, comma L2, and then Y1. You're telling it the X and Y values and where you want the calculator to store that data. So I'll type, I'm looking for L1, which is right here. As you can see, it is in yellow, so I have to hit second L1, and then I need comma, and then second L2. So I'm telling it use the L1 for the input data, L2 for the output data value, and then comma, store the whole thing in Y1. In order to find Y1, you actually have to hit variables here, and then Y variables, so move over one, and then function variables is the first one, so I can just hit enter. And then Y1 is the function variable that I actually want to use, so I'll just hit enter. Now when I hit enter, it's going to take that data from L1 and L2, create the linear regression using L1 and L2, and then store it in Y1. So it produced the same result, and it's also in the Y editor now a very, very accurate value that I didn't have to type in all those decimal points. It's stored automatically for me. Now I want to graph it, but before I graph it, I want to think about what's an appropriate window. So let's go to the window, and this is a good window here to go from 0 to 20 because my X values are actually the age of the child, so that's a good interval for that. This is counting by 5. And then from 0 to 20,000 is also a good interval for the Y scale because look at the data value from 13,000 to 14,000. I mean, I could start at 13,000 and finish at 14,000, but it just maybe better visual. Yeah, it's really your choice here is to be able to see the data. And I've chosen to go from 0 to 20,000, and I'm counting by 1,000. So actually in the graph now I actually see the line. One of the other things that this question specifically asks for is to also graph the data itself. So in order to do that, what you could do is hit, you see how right above the Y editor it says stat plot. So we can plot the stat data. So you hit, because it's in yellow, second stat plot, and then the first stat plot I'll just turn on. I can have multiple stat plots running simultaneously. I only need one. So just hit enter on plot 1, and then hit enter again to actually highlight the on. And I want to use L1 for the X list, L2 for the Y list. I'll use these little boxes, and this is for a scatter plot, and that's all we're gonna need here. So that hit enter. Oh, and then quit from that. And then when I go back to the graph, I actually also have the data and the line, and you can see, yeah, it's a pretty good fit. So that's really answering part C. It says graph the data set with the regression line. Is the line a good approximation of the relationship given by the data? And I would say, yeah, sure, of course. Okay, and now you can see part D. Part D says identify the slope and the Y-intercept of the model and interpret the meaning in the context of this application. So looking at my Y editor, I have, now I don't want to write all those decimal points when I write it out, so I'm just going to say the expenditure as a function of age is approximately 81.26 times the age plus, and let's go 13104.14, so that we're rounding them both to about 2 decimal places. So now you can see the slope and the Y-intercept. That's the value when the age is 0. Okay, and then interpreting the meaning, this is basically telling me that each year the annual cost of a child is going up about $81. So that's the meaning for the slope, and then the meaning for the intercept is the annual expenditure when the age is 0. Okay, and that's the answer there for number 11. Let's move on to number 12. Okay, for number 12, for the following functions, find the x and y intercepts, identify the slope graph the equation and give the domain and range. Part A says f of x equals negative 1/2 x plus 5. Let's begin by finding the intercepts. Finding the intercepts, I make a t-chart. For the y-intercept, I make x0. For the x-intercept, I make y0. If I plug in x is 0, I'm going to get 5. And if I make y0, I'm making f of x 0. And in this case, I'll have to solve for x. So I'm going to write 0 is negative 1/2 x plus 5. Solving for x, subtract 5 from both sides. And multiply both sides by a negative 2. That way I have 10 on the left side, and negative 2 times negative 1/2 just cancels to 1. So I have x. So the x-intercept is 10. Now to graph that, I have a y-intercept at 5, so let's just put 5 here, and then maybe twice as far. We'll put 10 over there. This is the x-axis. This is the y-axis. I'll try to stay consistent on the same axis. So if I put 5 here, I would put negative 5 here. But I can make the x-axis a different scale. If this is 10 spaces, then I would go an equal amount of space to the left to put a negative 10 if I needed it. I only need these 2 points. This point is 0, 5. And this point is 10, 0. Because I know it's a line, I only need 2 points. So now I'll draw a line. So let's say the x-intercept, that's this point here. That's 10, 0. Sometimes I just write x equal 10. Sometimes I write it as a point. Writing it as a point, I have 10, 0. The y-intercept, that's where you cross the y-axis. Where x is 0, that would be this point 0, 5. Also ask for the slope. The slope is easy to identify in this particular example because it's got the form y equals mx plus b, and so the m is negative 1/2. So I'll write it like that. Graph the equation, give the domain and the range. For this function, the natural domain is the entire real axis, entire x-axis, all values. There's no restrictions on what you can plug in here. You can plug any x value in, minus infinity to positive infinity. That's the domain. And the range, because this is a line that has a non-zero slope, it goes up and down forever. So that's the range, minus infinity to infinity. Okay, that's part A. Let's look at part B. This will be a quick one because the first thing you might notice here is that we've only got y. We don't have 2 variables here. We only have 1 variable. So this is going to be either vertical or horizontal. In this case, it's going to be horizontal because it's only a y value. So if we solve for y, we can simplify here. We'll get 3y equal 15. That's after subtracting 2 on both sides. So y equal 5. So this is actually a simplified version of this equation. It's very easy to graph, y equal 5. What happens with y equal 5 is I have constantly all the points where y is 5. I'm graphing all the points where the y is 5. This is the x-axis. Here's the y-axis. And I get a horizontal line. There's infinitely many points on here, but all I have to really do is plot one in order to draw it. Technically, you need 2 points for a line, but because it's horizontal, I just draw a horizontal line through y equal 5. So x-intercept, in this case, none, because it doesn't cross the x-axis. Y-intercept, you could say y equal 5, or you could write it as a point. Let's say y 0, 5 is the actual point. The slope of a horizontal line is 0. That's always 0 slope for a horizontal line. By the way, vertical line, undefined slope. This function, you could write it as f of x equal 5, is a constant function. You can plug any x value in and you always get 5. So the domain is minus infinity to infinity. But the range is only one single value, so I'll use the brace to say just the number 5. And that's the answer for number 12. And that is the end of the video. So I hope it was helpful. Thanks for watching.